All right. So yeah, to end this first part on high form symmetries, well, I couldn't find anything like new, very new on Simon's lectures, so I decided to check a bit the literature. And there is this paper by Nabil, Iqbal, and John McGreevy on Landau theory for one form symmetries that they call main string field theory, which is not really string theory, as we'll see. It's much more easier. So yeah, that's the goal of today, to understand how to generalize this principle to one-form symmetries. So what's the plan? So the plan is to understand, well, what we want to generalize and to review some conventional mean-field theory, which I mean by that is the zero-form case. And what they did in their paper is that they really, by analogy, constructed the one-form symmetry case. The most straightforward one that you can think of. And then we can study, once we have the action constructed and well-defined, then we can study the different phases. So that's the idea. Okay, so let's review this Landau principle. So we really like symmetries because, well, they're really useful to describe the physics, and in particular, it constrains a lot the theory and everything. But it's also important to study spontaneous symmetry breaking, right? Because different phases of matter are can be understood through this process. And we know that continuous phase are described by universal theory. You have this universal critical exponent. We don't care about the microscopic details, and it only depends on the symmetry and how you break them. So the idea is to generalize this to higher form symmetries, how we can break one form symmetry and what do we obtain from it. So another very important object in this idea is the order parameter, right? Because the idea is to write an effective field theory for this order parameter, and uh, and that describes the different phases. So in one phase, this order parameter is zero, and in the other phases, it's non-zero, like the broken and unbroken phase. But this is all connected to the fact that the particle will condensate, right? So this is already a bit tricky question in the context of one form, because now you have one-dimensional object, and how can you describe a condensate of strings? And this is where I want to point out that we are not studying fundamental strings, so we'll not try to have a non-perturbative description of how strings interact. We will really construct a mean field that is valid only until a certain cutoff. Okay, so that's the main goal, but I think it will become clear once we understand how to do it with zero form symmetries. Let me just, yes. Okay, so we have a zero form symmetry that we will spontaneously break, and we want to describe the different phases. So how do we do it? We take our degree of freedom, which is now a field, and it is charged under the U1 symmetry. Means that, after that, I guess, said in his first talk, that it's transformed linearly under the U1 group. So you have this transformation that you've seen with Q is the charge. So we really need to think about this field not as a fundamental degree of freedom, as I said, and this will be important for the one form case, and it is really valid until some scale lambda. And we know we can interpret it as creating a particle at the space-time position x, where the U1 charge counts the number of particles that we have. Okay, and we can also couple this U1 symmetry to a fixed external gauge field by promoting this to a local space-time function, and this is the gauge field that we had in the other talks. So the simplest Euclidean actions invariant under these symmetries is the usual one, with d the covariant derivative, and we have a potential that goes like m squared phi squared and lambda phi to the cube. That's the basis we'll consider in order to describe the different faces. And it's depend on the sign of m squared, right? Because if you have m squared positive, you have just this. Can I have a pointer with this? Cannot see my mouse. Then if you have m squared positive, you have the minimum at phi equals 0, right? And we say that the system is gapped. It just means that could we go from the ground state to the first excited state, you have a gap energy because it's a massive particle. And you can compute the two-point function in the limit where you have large scale separation, and you can prove that it decays exponentially, meaning that we are in the unbroken phase. So this you can show, I didn't show it, but you can show by really defining the two-point function. So you need to use the fact that you have a big separation scale. X minus 1 is very large compared to what? Compared to the mass of the particles. And then you can solve the integral by saddle point. And this is basically what you have. Work psi can be understood as the correlation length in your system. And it goes like m to the minus 1. And from there, you can also understood the critical exponent of this correlation length as being minus 1, 1 over 2, right? Because it's the mass squared minus the critical mass, everything in the square root. Okay, so that's the easy case where nothing really happens. But in the other case where m squared is negative, you can tell that the minimum of your potential is now at non-zero value for the field, right? So it gets a VEV. And you can compute the two-point function again for this field. And what you obtain is now it's a constant equal to the VEV of the field, right? So it factorizes that the VEV of phi dagger times the VEV of phi. Okay, so this is known as spontaneous symmetry breaking now because you have degenerate ground state, right? You have a family of them. I mean, here it's a 2D picture, but you can imagine a 3D. It's the famous Mexican hat potential, and so you have an old circle of degenerate ground states. So if you pick one, you really like break the symmetry. You need to choose one, for example, equals to V, or then you can rotate, and then you have a different phase. So that's basically what the Goldstone represent. That's different phases around this ground states that are written as theta. So you can rewrite your field as such, v exponential of I theta. And if you expand the action, so in particular the quadratic term, with this field, you obtain v squared d theta squared, which is basically the kinetic term for your Goldstone mode. Right, so this is how we see that we are in the broken phase and the field gets a wave, the correlation function does not decay, and we have a Goldstone boson. And we can understand this also phi as an order parameter for our theory. Okay, so if this is clear, I think it's really a standard theory, we can generalize it. But we need to define some stuff before. Because now we don't have a field, but we have a functional defined on the space of closed curved. So now the fundamental object is a functional, right? That takes a closed curve that we can call loops or closed string, whatever. This is our new object with which we will describe the theory. Okay, because it's, yeah, as Joe said last week, that's the fundamental object invariant under the one-form symmetry. So how do we extract information from this functional? So first of all, let's build some analogies. So yeah, instead of a field, we have now a functional defined on a closed curve instead of points. We know how it transforms. It transforms in a very similar way. So we have the exponential of now lambda instead of alpha. where it is a one form, a closed one form in this situation, and we can interpret this functional as creating a string living on that curve instead of a particle living on a certain point. And the U1 charge can still count the number of strings we have in our theory. But we are missing some information here because how do we build this action for this functional? We need to define a kinetic term first, and the kinetic term required to define a derivative of this functional with respect to something. And in the action, we will also need to generalize the volume element, the dx, and how to couple this to a background field and how to have an invariant object. Oh, there's someone with the mic. Okay, so I think the new concept here, it's the area derivative. That's what you use in order to, well, take the derivative of your string field. I think it's not a new idea. I mean, in the paper, it was mentioned that it's appeared a long time ago for loop formulation of non-Nabil engaged series. So if someone knows what that means. And the idea is very similar to the usual derivative that we can for a function. So you defined a curve C, and at some point in that curve, on the point lambda, you attach another small curve, right? And you need to take the difference of this functional evaluated as this extended curve, so the union of C and delta C, minus the regional functional on C, divided by what is called the area, which is the simplest geometrical invariant associated with this little bit of curve delta C. And this is really how they define the area derivative of a functional with respect to the area. So in the bottom here, I really cannot have a pointer. This is how you define the area on delta C. That's the second order in the sense that you could have defined the closed integral over dx nu, but this is zero because it's a closed curve. But you also have a higher contribution that we will not consider, higher derivative. That's the simplest one. And you can see that it is anti-symmetric because if you try to build the symmetric part, it's just zero again. Okay, so let's make an example to be sure we understand how to take the derivative of a functional. So
Just
here,
something with the previous slide.
yeah.
Sorry. Are we taking any sort of limit on delta C, say in like a
Yes,
standard
no.
derivative normally?
Yeah, this is
Yeah. So do we take
delta C small.
hmm,
Yes.
okay.
Yeah.
So it'd
So
be like some sort of delta C to zero. Yeah, that's fine.
yeah. So
Do you have a motivation for where the formulation for sigma comes from? So like what does sigma mean?
sigma. Oh, it's
Like you
the
say, yeah,
that's the area, right?
that's an area. Okay.
That the area associated with this delta C curve. That's the minimal area
Hmm.
inside the inside. Okay, that the
Oh,
area
I
is
see.
bounded by
Yeah.
delta C, right? And we
Yeah.
consider
So
it
is the
minimal, like the minimal one.
I see. So
So we
it's
can
like
think
the
of,
formula. Oh, sorry,
mhm.
I think we're a bit out of sync, so I keep cutting you off. But is the formula down there just basically an application of what's it, Stokes' theorem, where basically you're computing the area, but to
Yeah,
do it, you're doing it over the boundary. Is that right?
yes, exactly. Yeah.
Okay, cool.
Yeah.
Nice. Thank you. Yeah, and it's also intrinsic definition, which is cool.
Mm-hmm.
Sorry, just a quick question. So the choice of point lambda on the loop C is a sort of a directional derivative choice, right? In some sense. Because I guess the result for the derivative does depend on this point lambda in general, right?
Yeah, exactly. We need to pick a point. Yeah, because in this example, then you derive everything, and then at the end, you say, okay, for a specific point, then you have the derivative associated with it.
Okay, got it. Okay.
Yeah. Are you muted? Can't hear anything.
Oh yeah, just one final thing. With the formula you have on the bottom right, is that just an application of the chain the
Yes,
product
yes.
rule, or
Yeah, exactly. Simple as that.
yeah. Oh, I see. You just kind of switch them around. That's fine.
Yeah.
Yeah, cool. Thanks.
So you cannot have any symmetric part.
Mm-hmm.
That we will use when we derive exactly this example.
Yeah, I see. Thanks.
Okay, so that's okay, so let's consider this functional, like we couple this curve with an external gauge field, one form, and we just apply the definition. So we compute the difference of the functional evaluated at this extended, original plus little curve minus the original one. So, well, the contour is now delta c because the difference c cancel. And we will expand this at the point where we attach the curve. That's the idea. So that's the first order. I guess you have other corrections. And this is what I mean also by adding other terms to sigma. But for the moment, we don't care. We just take the first order. And this is equivalent to the second line here, where I've just defined x naught minus x as, for example, x tilde. This is how you can get rid of this. And you anti-symmetrize this del mu a mu, because you know that sigma is antisymmetric. So you can find this function. The minus sign comes from the x naught minus x if you do the change of variable. And then you obtain exactly this, where you have f defined as the derivative, exterior derivative of a, which is the field strength. So what you find by taking the area derivative of this coupling to the gauge field is the field strength, like the F associated with it. And so if we evaluate this for a generic point on the curve, this is the formula at the bottom here for this example. Okay. So a little side comment maybe that I did, we consider the minimal area, right? So it's the area bounded by C or delta C, depending on the contour you choose. But it's, yeah, well, a comment might be that it's not a local object. But the idea is, since it's minimal, if you vary it a little bit, like it will be stationary under small change in the curve. So in the end, only the boundary will change, not the area inside. So you can rewrite the variation of the area with respect to this area derivative in terms of local object, like the normal vector to the curve and the tangent vector to the curve. Yeah, sorry, I forgot to make a slide about it, but just in terms of local, non-local object. Okay, but now we have a nice definition of how to take the derivative, and we can also generalize the measure in our functional. So there's a weighted every curve by the perimeter, and this the motivation behind this is not honestly quite clear, but I guess it has to do with what we talked about last week, right? Because the web of field in the with uniform case is quite clear. I mean, you can always renormalize the field and you will get a constant. It's going to be a different constant, but it's still a constant. But here, like the web of a loop, it's maybe ill-defined, right? So you can always modify your curve by this little counter term, which is the perimeter of your curve. So I guess this is what they are taking into account. That would be the leading one. So in the action at the end, we will have this additional parameter that enters.
Sorry, just a quick question about that. So mathematically, I guess one can just say there's no Lebesgue measure, right? Because we're in infinite dimension now compared to the ddx, right? So you need somehow to put an extra decaying weight to have a well-defined measure on the space of loops, I guess. It's the same problem as in field theory, right? That you cannot define a measure for the functional integral, but the data of the kinetic term typically contained in the action just saves you because it decays quadratically at infinity, and it allows to give a meaning to the measure. I think it's the same problem here, but
yeah.
okay.
Yeah, probably. Yeah, I see it. I mean, that would be the right. You can for sure add more term in this exponential, like more curvature, but they are maybe suppressed compared to this one because M is supposed to be the cutoff, UV cutoff.
Right. Yeah, I think in general, on functional spaces, picking L to be quadratic is sort of canonical in a way because you get this Gaussian measure. But yeah, you can definitely add interaction terms, and yeah, it's just that mathematicians, they just don't know how to define it properly. But yeah.
Yeah, interesting. Yeah, okay, so to suppress a very long curve.
Right.
Okay. And so we can also couple this to a background field and build a covariant derivative, covariant area derivative, maybe we can call it. And we can check that the bottom equation is invariant under this transformation. Right, so I think we have all the ingredients we need to construct the action, and this is what they've called the mean string field theory. So this is where we put everything together. So we integrate over the space of curve, closed curve. This is the DC that we can replace. We can build our invariant kinetic term plus a potential that we will take it like that, like the zero form symmetry. And they mentioned that you can also add more complicated term that's include the merging of two loops, like interactions between the strings, because it's allowed by the symmetry. But in the end, like we will remove it. I just want to mention that in theory, this is a very general action, including those terms with the delta function of the curve. So yeah, it would explain that the interaction and the fact that it can merge to a larger one, but there is no like zero form intuition like analogy. Okay, so we will just consider this action with kinetic term plus potential here. And as before, we can ask what is the different phases of this theory, and it will again depend on the sign of R. So that's the first part. And
Just
what are
quickly,
yeah.
if you go back, what is STC? What's that action?
That's the one below with
Yeah.
the delta function.
Oh, I see the tiny one.
Yeah, sorry.
Yeah. What's that meant to represent?
Topology changing interaction, where two
I
strings can
see.
merge to form like a bigger one.
Yeah, cool. Thank you.
But I think you can prove that symmetry allows it, so that should be included in theory to have a full description. But we will not consider it to study the faces. Okay, so let's consider the unbroken phase, sorry, where R is positive. So as usual, we can have maybe a constant solution where this constant is to vanish in the unbroken phase. But they've shown that actually you also have more solution than that. You have all the functional that satisfies the area law. And so in order to do that, you need to compute the equation of motion, which is a tricky computation because, well, you have all this area derivative and you have all this. Oh, did I mention S is the proper length on the curve. Maybe it was defined here before. Yes. So you can also parameterize it with respect to lambda, right? It's just another way to write the integral over the curve. So yeah, this is what you obtain if you compute the equation of motion. There are some details in the paper. And so they didn't manage to solve it like without making any assumptions. So what they did is that they suggested to you this on that, where you have the functional of the curve C at the exponential of a function of the area. So they've already assumed that it's going to be a function of the area. I guess it's motivated by what we've seen last week. And this is valid if you consider large curve, right? This is where the approximation is. We need a large curve. And if you do so, then you plug this answer in the equation of motion, and at leading order, when you throw away a few terms, then you obtain at leading order the square root of r times the minimal area as a solution, where you can interpret square root of r as a string tension. So it's very similar as what we found before, but I mean everything is built such that it's similar. So that's very surprising. Okay,
What is
so
S in this context?
it's the same as before. Yeah, I mean the one, yeah, I define here with lambda if you prefer a parameter curve, right?
Can I?
Well, the dot is the derivative with respect to lambda, right? It's the
Oh, I don't mean that S, sorry. I mean the one that's in the ansatz. So there's like a curly S.
yeah, it's a function of the minimal area of the curve. Like we suppose it's going to be a function of A. We don't know what it is. And then you do double KB. I mean, you can solve this. You plug this in and you find that the leading one is linear in the area with the square root of R.
So
Yes,
is A the area in this context, not the gauge field?
yeah, it's the area. Yes.
Yeah.
Yes.
What if you plug the perimeter instead of the area in the ansatz? Is there any interesting solutions?
Well, I mean, in the unbroken phase, the wave function, it should satisfy the area law. I guess that's why the
Yeah,
dot.
I know.
But if they plug your perimeter in it, well, I don't know. But then you have the derivative, which is, well, yes. Yeah, not sure.
So L of C in this regularizing factor is the length of the curve.
Yes, exactly.
Okay.
Integral over
Yeah.
the measure.
Okay, thanks.
Yeah. But yeah, I guess I wanted to anticipate this area behavior, but yeah, good question. Okay, so that's the unbroken phase. So we allowed every functional to satisfy the area law. But in the broken phase, then it's again similar. So we consider R equals to zero, negative, sorry. And so we find a minimal for V equals minus 2R divided by U. That's the magnitude of the minimum, that's the position. And I guess that's the point where it is important maybe to include this STC, topological change, the other action that I've neglected, because that might change the position of the minimum, but that's it. But now we have a new minimum and we have a family of them. And as before, we can reparameterize the functional as this VEF times the exponential of I integral over A, where A now is a function of space-time. So that would be the analog of our constant boson before. So if we want to really see the presence of the Goldstone as before, we can plug this into our quadratic action, expand it okay, so you plug this in and you want an effective theory for A. So what you need to do is, well, you need to perform this integral over the space of curve, which is, again, I didn't really have time to go through all the steps, but you can do it. You need, I think, to go to the Fourier space and use some normalization that nicely leads you to this action on the right. So what you obtain is that the leading order, and that's the Maxwell kinetic term for the gauge field. And so as before, we can really see the presence of the Goldstone boson. So this is, okay, so you have this Mexican hat potential. So you know that going uphill, it's like it requires some energy. So we just go around the different minimums. So we parameterize these phases, right? We don't touch the magnitude. We just reparameterize the phase to go around the different minimum. So that's what the Goldstone here. That's what I mean by the modulation of the string field. It's really, you modify the phase because that's where the Goldstone is. Okay, so that's
Just with this, do you know what how F mu nu is written in terms of A or any
it's
of the other
derivative of A.
the exterior derivative A?
Yeah,
Okay.
the D, A. Yeah.
Mm-hmm. Cool. Thank you.
Okay. So yeah, that's the main idea of what I wanted to present on this topic.
Actually, sorry, one other question just to back
Yeah.
to that one. So I've heard that they can describe the photon as a Goldstone mode of the
Yeah,
Maxwell
that's the
theory.
Goldstone. Yeah.
Yeah. Okay. So is this basically the same idea?
Yeah, that's exactly what it is.
Cool.
Yes,
Nice.
in that case.
But say in a Maxwell context, where exactly is, say, the string action, or where would that come from? Do you have an idea about that? Because like we started with a string action here,
Yeah.
and then we looked for the Goldstone modes from, you know, the spontaneous symmetry breaking of the string action. But in Maxwell theory, I don't see if it's necessarily, if we can write it as a string action. Maybe we can, I'm not sure.
Yeah,
But
that would be the other way around
yeah,
then.
yeah. So I guess that's a good question if we can write it as a string action.
Well,
Maybe we
sorry.
can't, but I don't know.
Wouldn't in the Maxwell case you would just write the Wilson line,
Yeah.
and that's sort of the original I. So you mentioned earlier, well, you didn't mention him, but that's McDowell, and he had this idea long ago of sort of trying to solve QCD using the ideas you're mentioning here. But yeah, it would just be the Wilson line.
Yeah,
I mean,
that's a good point. Yeah.
A here is a function of space-time, but then if you shift it, it's really like the one-form symmetry in the Wilson line.
I see.
If you include the shift. But yeah, that was the first part of the paper. Well, I'm happy to redo this computation with you just here. Also with the slide, it's quite horrible to read equations and to follow. So yeah, and that's what the main idea. And then I think it's very interesting framework when you can learn a lot of things about about one form symmetry using this global like idea of Landau. And so I think they want to use it to maybe find new artifacts points. And I think, a lot of needs to be done because, for example, all the NSAT that they've done, they did a lot of numerics to get some intuition about what's happening. So I guess a lot of work remain to be done. But yeah, that's all I wanted to say. Happy to discuss more.
Sorry, can I ask a question?
Yeah.
Do you know if we can redo this entire story for non-abelian theory?
I would say yes, but haven't found any, didn't look for any paper.
I see. Okay. Yeah, I was just wondering during the beginning where you showed us this derivative with respect to that.
Yes, exactly. That was first introduced for non-abelian gauge theory, so
Oh, I see. I see. Okay. So
probably there are, yeah, more about it.
okay, thank you.
Mm.
I'm just thinking in terms of, say, expressing Maxwell gauge theory as a string theory in terms of the Wilson lines. Well, in that sense, then we would have the negative parameter. We would have r less than 0. But I'm just wondering, suppose, I mean, I guess depends where r fits into it. But like, if we could then vary r to be positive, I wonder what sort of theory that corresponds to. You know, like this, is this some sort, like how does
Unbroken
ordinary,
is like the Coulomb
yeah,
phase, right?
yeah.
And then
Okay, sure.
yeah, I think you
But
can
say
involve
like,
the Higgs
yeah,
phase and the Coulomb phase by studying
hmm,
if this is well defined for like yeah, Maxwell in terms of string field. I guess you
yeah.
should recover the usual Coulomb phase and Higgs phase.
Maybe this is a misunderstanding on my part, but say like with the Higgs phase of Maxwell theory in this context with the Wilson line strings, and then the photon being the gauge broken, the Goldstone mode from the Higgs phase. What would be, say, like the corresponding field so that in the Coulomb phase then? Because, you know, Goldstone modes are an emergent property from spontaneous symmetry breaking. But then what does it mean to be in the Coulomb phase? Like you wouldn't have the photons then, or they would have some sort of other property. Would you just have like the Wilson lines as your fundamental property operators then? Or sorry, fields. I don't
Right.
know. I don't know if you can answer this, but
Right, I'm thinking. No, but what I understood from this, well, spontaneous symmetry breaking in the Maxwell case, yeah, it's yeah, you need to look at the the wave of your loop, right? No, because then this is where this parameter, I guess, enter the game, right? Because
hmm,
this, if you have the expectation value of your loop that decay or increase faster than the perimeter, I guess this is how you define if you're in the broken or unbroken phase, right?
yeah, yeah.
Well, even without the area law or whatever, I think it's yes. Don't know if I understood your question, but yeah, the two phases in Maxwell, I think you can um, distinguish them by looking at the expectation value of your loop, right?
I see.
As an order parameter, right?
Yeah.
So it should be 0 or decaying faster than the perimeter in the unbroken phase, um, and the inverse in the broken phase.
Yeah, okay, okay.
Just a quick question. I remember this notion of loop space. Like if you give yourself space, you look at the space of loops within that space. So the space of maps from S1 to the space, so to space-time in your case. And there was this idea, for instance, that if you take a principal bundle on loop space, it corresponds to taking like a gerb on the space. So which means that you would have a connection that's literally a two form. So it's your B mu nu connection. I'm just wondering whether one could try to write a standard Landau-Ginzburg model on loop space And this would reduce down to your Landau-Ginzburg model for strings on space. I don't know if it's clear what I'm saying. I'm trying to.
Okay.
So it was an old story from Witten, actually, when he was trying to understand this elliptic genus as a sort of index of a Dirac operator. I don't know if it's a familiar story to you.
Not really.
So yeah, sorry, maybe it deviates a bit, but there is sort of refined Witten index for supersymmetric field theories that carries extra operator insertion for any global symmetries your theory could carry. And the question is how to compute these objects efficiently. And it so happens that it's a topological invariance. And drawing inspiration from index-like theorems, you could imagine that this object could be the index of some differential operator on some bundle-like structure on your spacetime. And that's the question that Witten was trying to answer. And the answer is yes, it is, but it's not as trivial. So, but you need to look at the space of loops on your space, basically. So you replace your spacetime by the space of loops into your spacetime. So basically, you're looking at strings. And you're doing standard index theorem, but on that complicated space. And you get back the elliptic genus.
See.
So it reminded me just a bit of that because
Yeah, with this, yeah, I can see.
you see. So for instance, if you do a nonlinear sigma model with target the loop space, you would get in some sense, strings propagating on the space itself.
Yeah.
I'm just wondering whether the same philosophy could be applied to Landau-Ginzburg-like models of writing a Landau-Ginzburg model on the loop space, and it would basically reduce down to what you exposed, but it's just a bold guess.
Yeah, I don't know if they've done, if they commented on that. No, I don't remember reading something like that. But that must be, was it in their conference? Loop space, yeah.
Yeah, no worries, just a question like that.
Yeah, no, I didn't, don't remember anything about that. But yeah, it was only before first actions. The last one was about discrete symmetries, and maybe the last one. I didn't check, so maybe it's in there. Reformulation.
Just a general question. What was their motivation for considering this? Did they have a particular application in mind, say to a condensed matter system, or?
Well, I guess the challenge was more on building this.
I see, just from a theoretical perspective. Yeah, that's fair.
Yeah, like to generalize this principle.
Yeah.
But yeah, that it is. Yeah, I don't know. It sounds really too straightforward. But it works. I mean, but they do really what they have to do at the right. For example, that they assume that it's proportional to the area, because they couldn't solve it exactly. Sometimes it sounds a bit, well, not cheating, but
Yeah, very ad hoc.
Yes, but it's a
That's
nice formulation, I guess.
Yeah, that's true. Yeah, one other question I had, say, if you go back to your slide, I think it was a few slides back for the example one. So you had the example for the first one for phi. Yeah, this one here.
Yeah.
Could you walk through, say, the steps for doing the computation for the derivative where you do phi c cup
Yeah.
dc minus phi c? Like, how do you get that from
Um,
the line above? So you've got how do you get the second line from the first one?
right. Well, you need
So the
to
first is like an OPE, right? Something like that.
nice Taylor expansion around the x
Oh
naught.
yeah.
Yeah, there is no tricky part. X naught minus x, you can rename that x. x tilde. Okay, maybe I was lazy with indices. This is not the same x as before. This is why you have a minus sign.
Okay. Yeah.
And then you antisymmetrize your then new a mu. Because you want an antisymmetric tensor at the end. So
Yeah.
like you add it divided by 2, and then you can switch the sign, and you have your
Mm-hmm.
antisymmetric f. Not f is symmetric, but antisymmetric.
Where do you get the total derivatives? You have dx mu. Like, where does that come from?
dx mu.
So it's like minus a half.
That's my measure also. Okay, sorry. This is okay.
Oh,
I've
okay.
got it here, but in the first equation, you can see it's like in the definition of phi, right?
Yeah. Oh, so
So
it's meant to be
this
in
comes
the
from before. This
one
comes from
above.
before. And
Hmm.
right, missing a dx mu.
Oh, I see. Okay, that makes more sense. Cool. And then yeah, I see that. That's fine.
Yeah, that's really not complicated.
Yeah, thanks for that. That makes
And
more
the
sense.
first term is 0 because it's a closed loop and you integrate
Mm.
like constant. So, I mean, yeah, the one form.
Yeah.
Sorry. Okay. But yeah, we can, I don't know what we're doing next week, but we can organize like a exercise session if you want to derive more equations, since it's a bit the transition. So maybe. But yeah, any more questions on this?
In the old days of string field theory, wasn't there this claim that somehow open strings were easier to treat than closed string? Or I'm not very familiar with it, but I think I remember such a claim that somehow open strings were easier to describe in a field theory framework.
Well, I don't know where that would make a difference. Because if we think about Maxwell, I mean,
Yeah.
we would need like infinite strings and
Right.
to be charged. Or here we take the large loop in the sense that it would go like to a infinite
Yeah.
string. But I don't know if you can do the same computation with open strings.
Mm.
Probably not well defined.
Yeah.
I mean, you would need then, I don't know.
I mean, this construction probably doesn't really make much sense if you think
Yeah.
about open strings, because like we're talking about these one-form symmetries,
Right.
and naturally, if it's an open string, these topological operators are circles and they just detach.
Oh yeah, right. They would have to
So-
end on some charge matter, right?
Yeah.
Yeah.
But I think in this construction, you're considering just the pure theory of the loops.
Right.
But if you had matter, then yes, it's
Yeah.
more complicated, but maybe you can.
Yeah. I was just wondering technically, like, why in these old days of open string field theory, like, yes, open string was just easier to treat than closed string. Technically, I just don't know. But yeah, they were treating basically merging of strings, which is the term that you described.
The one here. Oh,
Yeah, I guess the difficulty comes from there. Right.
yeah, here we neglect any interaction between those things.
In the paper, did they try to reintegrate that term to see what happens at the level of the equation of motion, for instance?
Maybe in the two last sections. But to
Okay.
say the phase of the series, they didn't need it. I mean, they really assumed that it wasn't important.
Right. Okay. Yeah, thank you for the nice talk.
Thanks.
So in this one also we didn't couple to, like we just have it as a global U1 symmetry and then, well, U1 one form symmetry, but then we don't couple. Do you know what would happen, say, if we gauge it? Like, how does that change? We have the gauge
The
covariant
D, the
derivatives, but
covariant is this guy,
yeah.
right?
Oh, you've got the B fields. Are those going to be your
Yeah.
gauge fields? Okay.
Yeah,
Yeah,
so you
okay.
call it. Yeah.
Yeah, that makes sense. Okay. Oh, and I see you've got the one form symmetry there with the e to the I q integral of the lambda.
of this one. Yeah,
And lambda is a one form, right? Is
yeah,
that
yeah,
correct?
exactly.
So then B is going to be a two form gauge field.
Yeah, yeah, alpha beta index. Yes. Yeah.
Yes.
Do you know if anyone's looked at a supersymmetric version of this? I'd be interested in what like a one-form supercharge would look like.
Oosh. No, no, no. No.
Because I guess it's like bosonic string field theory, right? Just purely bosonic. Like even those fields there that you have psi are just scalar fields. Well, not fields, but scalar one-form operators, right?
Sorry, what? The,
Those psi operators that you have,
yeah,
which
that's
act
my
on,
functional.
yeah, sure, uh, but they don't have any fermionic nature to them.
No, no.
Yeah.
They do work, but I didn't. Yeah. There is a condition on psi, though. Yeah. So no, I don't know anything about supersymmetric story. Well, I guess this is not even completely understood, so I'm not sure the study the supersymmetric case.
I guess if there's no other questions, thank you very much. It was a very nice talk, I think.
Thank you, thank you. I didn't know, yeah, if I was ready or not. I mean, I wanted to tell more about this, but I guess, well, you can go check the paper. But yeah, it's very interesting. I really like this.
I thought it was quite nice.
What did you want to mention, Adele? I'm happy to listen for this.
Well, I don't have any slides, but I can show you the paper.
Okay, yeah,
Yeah.
happy to just listen. Or we could look at the paper if you want to chat about particular things.
Yeah, but my keyboard is not working.
Okay.
Can't even like, yeah, do anything. This is why I don't have my pointer or anything.
Yeah.
I don't know. I need maybe to. Aha, here we go.
Oh, cool.
Yeah, that was derivation, but it's yeah, it's quite detailed. It's only this part. Indeed. Well, here that was the final
Do you know what section of the paper it is for the
4.2,
derivation of that?
4.2 section, page 25.
Page 25. Okay, let me have a look.
So
Do you know
the
what would happen if you include the topology changing terms? So for example, like we've neglected that, but like
yeah, this they're not considering it. Maybe after. But yeah, I
they
guess the
just
key
kind of
point
ignored it.
is you derive the functional with respect to the area again, and you use the fact that you know that it is the two form, right? The extra derivative of A, because A is a one form.
Yeah.
I mean, it's a space-time function. So
Oh, I see. They go into the Fourier transform and then they
yeah,
compute
exactly.
that.
And
Yeah.
then they define in the Fourier space what's that, and why it's quite. I don't know if we want to have a look at it here.
Yeah, we only see the slides, but I'm just looking at the paper separately. Cool. Okay.
Yeah, I get the key point is this derivative, you go to Fourier space and missing simplify. But yeah, to the right, yeah, maybe to mention, since we have the paper here, in this derivation of the unbroken phase, right? Sorry, you have the ansatz in the equation of motion, and so you get this, right? But here they also neglected that term, for example, because they said that at worst it will grow like that. So you can
I think we only see the slides, but I can see
gosh.
your mouse moving around.
Okay. Um,
I think
yeah.
you need to reshare screen. Like just
Indeed.
turn off sharing and then
Stop sharing. Yeah, sorry. Okay. Now to derive this form for the unbroken phase, right? So they did some approximation. So you have this ansatz that you plug in your equation of motion, and basically what you obtain is by doing this WKB type is this equation. But then they removed that term. So you know there are several steps where they approximate and they say, oh, maybe this one is less important than this one because it will grow like that, especially. That was their argument. So you can basically remove it, and that's why you have S prime equals R.
Mhm.
If you want to go in the details. But yeah. But yeah, so the last two sections, I don't know if it was discrete symmetries and the consequence of the emergent one form. This I didn't check.
Yeah.
On a next talk, maybe.